and observations to an actual computational model. So these slides are already online, and also the codes that I'm going to use. So if you go to the CompuCell website, to the workshop page, then there is a link for the class files, which is a link to Google Drive, and it should be there, everything. Yeah, workshop page, then the second link is the one to the files. Yeah. Okay. So for the actual presentation. So I'm going to try to make it more of a guided tour of how to go in from biology to code, because that's not simple nor obvious how to do. Yes, I think they are actually seeing my screen, so they are seeing the presenter's view. So whatever. Okay. Going from biology to simulation. In this case, I'm talking about the avascular tumor, which is a in vitro experiment where you have a cancer. And you have observations about that tumor. You know that it has a necrotic core, some quiescent cells, some proliferating cells on the outside. You know that there's nutrients, oxygen, etc., coming from the environment into the tumor that's being consumed. So the levels are going down as you go further inside. And the tumor is producing waste, and those levels are going up as you go further inside the tumor. But how do we translate those observations into code? So in this case, what we really care about is the distribution of chemicals. Then there's computational considerations. The tissue takes a while to respond to a chemical. So we need to somehow also translate that. And for instance, if the tissue starts to shrink, you don't want it to shrink faster than the chemical field updates. In case, well, you may want to do that, but you need to be observant of that. And you want your simulations to run fast. So there are more, you have to pick sizes for the simulation that makes sense. So CompuCell is a lattice space model. Each pixel represents a certain length or area. You could have a grosser pixel size, which is the top example there, but that will give you almost no detail of the cell. Then, okay, I'm gonna go finer. But if you go to 1 nanometer thick pixel, you're gonna need hundreds of thousands of pixels to simulate anything. So your simulation is gonna take forever if it runs. So there's a give and take there. Usually we say that voxels in CompuCell, their size is 1 to 5 micrometers. The same discussion is valid for time in CompuCell. We usually say that 1 Monte Carlo step is 1 minute, but if you make one Monte Carlo step be 10 minutes, you're not gonna see any of the behaviors that happen in the meanwhile. And if you make a Monte Carlo step take 1 second, again, your simulation is gonna take forever. So back to the tumor. Again, we know that it has a necrotic core, a quiescent layer, a proliferating outside. They are like that because of chemical concentrations that during this talk I'm gonna approximate everything by oxygen. So ATP, lack of waste, nutrients, everything I'm approximating as oxygen. And those chemicals diffuse in the environment. And how they diffuse inside and outside the tumor is different because the tumor is consuming that and the diffusion constants are different. Not so much for oxygen, but for the other ones. It's forming a seal, I think, yeah. But if I recall correctly, oxygen can just go through cells generally, more or less. But cells are uptaking oxygen, so that changes the diffusion length anyway. But yeah, so diffusion. Diffusion is things spreading out. What we care about diffusion is, here I have a movie example. So just a drop of ink diffusing. So what we care about diffusion are the diffusion length, diffusion time, and relaxation time. That again, we have to translate to code. And if we can set those properly, we can have the tumor be three-layered. If we make their cell types depend on chemical concentrations, and we know how the chemical concentrations change inside, we can change it properly. So here's the diffusion equation. What it has there is the diffusion constant, the decay constant, the concentration, sources, and sinks. So none of the stuff that we care about is there, which were diffusion length time and equilibration time. So how do we go from this to things that we can actually measure, care, and actually want to translate into computer code? Well, we are going to use dimensional analysis. Dimensional analysis, you just kind of solve the equation, but only taking care of the units of the stuff that are there. For instance, the accelerated movement there. We know that in the end we want a distance, and on the right side we have a velocity, a time, acceleration, and time again. We know that acceleration has units of meters per second squares, so we want meters in the end, so we need to multiply it by time squared. That's the idea of dimensional analysis. In the case of diffusion, those are the units. And I thought a exercise would be to actually find those. So here sigma is shorthand for sources and sinks. So now you could take 2 minutes to find the units of D, gamma, and sigma, I think. D has diffusion and has meters squared per second in my view, because if you imagine a droplet of ink diffusing, it's going to diffuse radially. So it's kind of the increase in area in time. Area. Yeah, that's my interpretation. Might not even be a good one. And then sources and sinks have to have the same unit as concentration per time, which makes sense. They either put in a certain amount of concentration each time or take out. So yeah, you're right, those are the units. Okay, so now we have the units of the gamma and sources. But still, we need to relate those to diffusion length, diffusion time, and equilibration time. So, diffusion length. Diffusion length, as the name implies, is a distance. So, we want meters in there somewhere. We already know that the diffusion constant is meters squared per second. So that has too many distances in it and time that we want to get rid of. Gamma has seconds, so that allows us to get rid of the seconds if we divide d by gamma. Then we are left with meters squared, so we just get the square root of that and we get the diffusion length. Not that hard. Yeah. Hmm? Yes. Yeah, but we thought that this was straightforward and quick. But yeah, you're right. The diffusion length might not be that exactly. But for us, it is. Yeah, it will be proportional. Yeah, most cases it will be that. If you have actual uptake should be in there somewhere. Kind of how gamma is there. And sinks in general will also influence the diffusion length.
But gamma could be 0.
Yes. Gamma could be 0. Then the diffusion length is infinite if you have no uptake or sinks. Yeah, forever. Well, the steady state is concentration over the size of the universe. Then diffusion time. So diffusion time is the time it takes the concentration to go from point A to point B. So because it's a distance from A to B, we need a distance there, but we want to get rid of that afterwards. Again, d has meters squared per second, so it has time there. So if we just square the distance this time, instead of getting the square root, and divide by d, we get diffusion time from A to B. And finally, equilibration time, the easiest of them all, it's 1 over gamma. So going back to gamma equals 0, it's common to put a tiny gamma even for things that don't decay. Oxygen doesn't decay, but we put a very tiny gamma with oxygen just to make it equilibrate faster. Because without gamma, the system will never forget the initial condition. And well, yeah, it will never equilibrate. No, you can set d to 0 or gamma to 0. Well, if you set d to 0, things will not change. If you are using the chemical fields as something else, that aren't chemicals, if you found that that's a good way to model something else, like, I don't know, ECM levels. Yeah, so then you can have d equals 0 and you have the ECM field be static. So here, table of the things we know so far. We know that we are going to have an environment in CompuCell with a chemical field. And the environment has a size. The chemical field has a diffusion, constant, decay, and initial values. So now to the first exercise. So this is a very simple exercise, no cells, just chemical diffusion. Chemical is set to, value is set to 100 on x equals 0 and 0 on x equal 100. And that is among the files there. If you can now open them. So again, getting to the files, CompuCell main page. Then there's a link to the workshop page here. That will take you here, where there's a link to the class files. It's the second one. And that's a Google Drive folder. And my stuff is in the Avascular Tumor class subfolder. And the path to this example is student materials, Avascular class, examples, concentration profile. Actually load it up. Not that one. And I actually have two examples here. One of them, I've actually seeded some cells in the middle that they are frozen, they do nothing. They just have a different set of diffusion constant and decay rate. Yeah, so on player, you're gonna open profile.cc3d. From the Google Drive directory, you have to download everything that is in there. So, just download everything inside examples. Because the .cc3d file is only a list of files that the player has to load afterwards. So with player, you're gonna open cc3d file, but it needs everything that is inside simulation as well. So I'm just gonna open it here. Leave it stop. That's what you should see after opening it. Yeah, you don't need to wait for me to actually run the simulation. You can set it to run already. And the main point of this part was, so here on the left, there is this control panel thing. If you go here to the steppables, I have the diffusion solver. Then in here, it has the chemical field, its diffusion data. So here you can change the diffusion constant and decay rate. So if I run this for a bit, it's gonna go forward. But I can then change this to a really big number, like 1. And it should change the behavior. Yeah, and it did. Yeah. Once you have this running, you can play around with the constants on the left panel and see how that changes the shape of the concentration at the end. The yellow dot there is the current diffusion length, because diffusion length is not the length to get to 0 concentration or the length to get to 10% of the concentration. Diffusion length is the length to get to 1 over E of the concentration. Is the diffusion length at this time step. No, here on the left, I have the diffusion data here. So things that we, yes. If they have, the only restriction is if they are a float, you need to type them as a float. So if you have 10.0, you then need to type 15.0, you can't just type 15, and vice versa. If you have an integer, you cannot make it a float. Yes, it's an integer. Well, in the calculations, it's going to be a float, but I can't type 20.5 here. It's going to go back to 20. Yeah. Yeah, it's a small annoyance. Yeah, now the system has stabilized to a straight line, but if I increase the decay rate by 100-fold, it's going to start to tilt downwards. And we can see how the diffusion length changes as well. Yep. Yeah, sources and sinks. So in this case, I have one source at x equals 0 set to concentration 100. Yeah. And then on maximum x, I have a sink with concentration set at 0. But maybe, yes. So I can actually change the values here. So I can go from 100 on the left to 50. And it's going to do that. And then stabilize again on a straight line. If I gonna set the decay to 0, then let's go to 10. You can kind of see the concentration being pushed to the right. And if there wasn't a sink on the right, that would never stabilize again. Because now everything extra that was there needs to be drained out. If there was no way to drain it out, it would just stay. So how can I do that? Put this back to 50. Let it go for a while. Yeah, I don't think in this example I can actually show it staying forever because both my sources are a constant value. So no matter what happens in the simulation, the concentration at that point is going to be that number. If I had the sources and sinks being constant flux, meaning that no matter what happens, each time step, it's either gonna put in a certain amount or take out a certain amount. I could show it by just turning off the sink and the source. So it's gonna put in and take out 0.
On the Fox model, I see that your Y dimension is 64.
Yeah.
Isn't that a waste? If there's no motion, that's symmetric. Motion in the Y direction.
Yeah. Yeah, I put it 64 just to have a certain, for visualization purpose. Yeah. But yeah, I could make it a pixel thin, but then we wouldn't be able to actually see it. Yeah. Yeah. Yes. Yeah, this is not actually POTS model. This is just the diffusion solver of CompuCell. Yeah. I'm gonna open up the next example of this. That is this basically the same thing, but with a barrier for diffusion. Here. So here I do have some cells, but still there's not going to be any pots because the cells are frozen. They are not going to change in any shape or form. They are just there because in CompuCell we can specify different diffusion constraints for different cell types or even cell IDs. So each individual cell could have their own thing. And you can also specify sources or sinks anywhere in the lattice. So in this one, the global constant is 20 with the global, yes? Yeah. Yeah. Because up here in visualization, I have selected cell borders. If I unselect that, important note about the cell borders is if you have a 3D simulation and you want to see it in 3D, remember to remove the cell borders before going to 3D. Because trying to render the borders in 3D is gonna kill CompuCell. So yeah, here the global constants are 20 with the decay being 2 times 10 to the minus 5. While in the barrier in the middle, the diffusion constant is 4 times less and the decay is bigger by 100 times. So in this case, it's not going to be a straight line from 0 to maximum max. Yeah, on to edit. Yeah. Just let it go for a bit, for the point of the thing. So there's a huge drop in the middle because of the slower diffusion constant and the higher decay. But yeah, on to edit, this one is the first simulation. Is that readable still? Yeah. Oh, no, it's not this profile. This one. So yeah, I only have a chemical field chem here on the XML with the set, global diffusion constant, and global decay constant. There are some more options that I left here, commented out. So you can have a initial concentration expression here. You can put anything or almost anything in there. So you could just put in a constant or sign of X if you want for your initial concentration. Down here are the actual boundary conditions that I could have constant value or constant derivative, which is constant flux. About what? Yeah. So constant value, in this case, at the minimum X, constant value means that no matter what happens with the simulation, you have a ton of cells in there consuming a billion kilos of oxygen each time step. It's going to stay at 100. Yeah. And then the periodic for Y only means that the chemical doesn't see the top of or bottom of Y. It goes through, like on asteroids or Pac-Man, those kind of games. So this simulation here, it's not actually a plane, it's a cylinder on Y. And you can also you can both have a constant value, constant flux, and make it be periodic. In that case, I think things are going to be a bit weird because you're going to have 100 right next to 0. But if you want to, and then the only thing I'm doing with Python is the actual plot of the concentration here. So this side here is the only thing I'm doing with Python.
There's 2 Pythons, right?
Yes. Steppables. We will never do anything with the other Python. Yeah. Which is a bad name, in my opinion. So yeah, when we say in the Python, it is steppables, no matter what. I don't think so, in this case. Let's see. So let me reopen that one. Yeah, same thing. Yeah. No, the plotter is PyQt graph. Yeah, so to actually add plots to CompuCell, something I can show now, I never remember all of that junk there. There's no way. So up here, if you go to CC3 Python, you have scientific plots. And then you have everything in there. So to add a plot window, you need to add it on the start function. That's the only restriction you need to take care of. So then you click setup, it's gonna paste everything in there. If you have more than one plot window, you need to actually name them differently, because now I have one plot win for plot window and another plot win for plot window. So maybe a more descriptive, if you're really lazy and want to give way more trouble for people that inherit your code afterwards, you can just have plot win 2, and so forth. Or you could have actual descriptive names. Plot win for, well, in this case, I only really have concentration, so. Then in here, in the arguments, you have the title of the plot window, what you want to label your axis, if you want the scale to be linear or log, and if you want a actual grid to show up, the backdrop grid there.
Would you specify the variable
So
defined?
for each of the variables you want to put there, you need a different one of these statements of adding plot. And each one of them need to have a unique string name as well. And in here, you specify the style of that. There's also lines here as an option besides dots. And I'm sure there are others. Yes, I'm going to. Then on the steppables here is where I'm putting the values there. So again, I don't remember how to do this. I go here, scientific plots, add data point. Data point. So you just need to pass the string of the plot you want to, are pasting to, value for X, value for Y. So here I'm putting in all of the concentrations going from the higher X to the lower X because of reasons. In here, where I'm actually finding the diffusion length, I have to specify that I want to write to the diffusion length. Yes, because in this case, I don't know if you notice here, yes. So in this case, I'm updating the title up there to be the diffusion length, just to make it more visible. But that's a optional thing.
If you want to do the mass function of time,
Yeah, you could.
not X, but T now, or something, right?
Yeah.
So as the simulation goes on, we're going more and more, using more and more stuff.
Yes. So you want to plot the total concentration. Yeah, we can do that. Mass. Just gonna leave that as is. So in this case, mass equals 0, then mass plus equals. Right, so here I'm only going through the x-axis and grabbing the middle of y instead of going throughout all of y, and then so what I can do, it's gonna be slower. Is that a 4 Y in range. In this case, I don't actually need to go backwards. So CompuCell already knows the dimensions of the lattice with the self.dim for dimension dot the axis you want. So you don't need to remember that you set Y to be 64 and go from in range 0, 64, and that I set X to, I don't know. CompuCell has that already. So mass plus equals, no. Yeah, so the first line in the steppables code is gonna be this, from CC3D core PySteppables import star. So there are several CompuCell names in here that are reserved for stuff. For instance, self.add new plot window, that comes from there. MCS comes from there, cell comes from there, self.celllist, self.dim.axis. So yeah, here now I have the mass. So now I just need to add a plot to this one that I had a mistake down here because I was adding another plot to the plot win instead of plot win mass. So dot and add data point. What did I call the thing? Mass. Then MCS and mass. Yeah, that should be it. Yeah.
You have to specify what your experiment is, or does it auto scale?
The plot window? Yeah, the plot window auto scales for everything. Yeah, it will go up. Well, not, I don't think it will go down unless you erase everything and plot again. But yeah, and in here, I also have this, each time I'm plotting the concentration, I'm erasing the concentration plot. Otherwise, there would be several lines of the concentration, which might be interesting to keep. So let's, I'm gonna comment that out. See here. Tile. So yeah, we can see that the mass has gone up from 20,000 to 200,000 already. And in this case, we have a timeline of how the concentration changed so far. The new plot on the left? Okay. So in here, first of all, I needed to add its setup function in the start. So I just went to CC3D Python, scientific plots setup. And it's gonna paste all of this thing. But each plot window needs a unique name here on the left of the variable. I'm already using plot win up here. So I renamed that one to plot win mass. And it also needs a unique name inside the arguments here. That in this case, I didn't bother changing. But mass. Then as parameters in this function, you have the title of the window and the names of your axis and some stylistic choices. But that creates the window. You still need to create the actual plot inside that window. And that's why this function here is there. So this function here is creating a plot named mass inside the plot window plot win mass. Yeah. The second one creates where you're gonna put the dots inside the window. So in this one of the concentration, I have two different plots inside of it because I'm both plotting the concentration itself and the single point where the diffusion length is. That's why I have two. So yeah, no, that's somewhere else. So the updating of the diffusion length is here because I'm resetting the title each time to be the length. Yep. For instance, if you are tracking cells centers of mass, you could plot y by x, or you could plot y and x by time. So if you want y and x by time, you need one of these for the y and another for the x. Yes. Yeah. Yeah, this function is going to add a set of points. Not actually a set of points, it's going to tell it how to plot a set of points. No, in the step functions, I'm just actually giving the points. So yeah, so in this case, let me just copy this down here to make it easier. So here I'm adding the plot concentration, and in here I'm adding a data point to the plot concentration. What? Yeah. It has to be in the start. I didn't add it to the step. I just brought it down here so that we could see both of them at the same time. Yeah. Yes. The plot setup needs to be in the start. And so if you here on scientific plots, it actually says setup start function. Yes.
Is it possible to open this up in PyChart and put in breakpoints and see what's happening?
Yes. I don't know how. Maciek does.
So you know when it's exactly what.
Okay. Yeah. So there is a function here on CC3 Python utilities simulation, stop simulation. So if you manage to write your if properly, you can stop it whenever you want. I don't know, if you have cell growth and you want to stop it once 99% of the medium is occupied, you can have if occupied space greater or equal than the volume, stop. In this case, it would be a bit harder to actually write the if. Yeah. Yeah, well, then might not be so hard, but yes. Yep. So the title is just the title. It's the same thing. I'm changing each time step for the diffusion length. This one is the identifier for this particular plot, but it could be that. Yeah, then you need to make sure that you're using this string here. Yeah. Okay. If everybody's happy, I'm going to go back to the tumor spheroid. So here in the XML, I can specify on the plane position. I don't know if we can use the XML to specify it anywhere, but if I want to specify a source in the middle of the lattice, I can just do self dot. By the way, I also don't need to remember all this field stuff because it is here. So here, chemical field manipulation, got everything. So here's set field value. So self field chem. Yeah, let's say from 10 to 45 and from 5 to 50. I want the concentration to be 75 forever. So if I run that now here, and I didn't mess up, got that constant concentration there. No. Yeah. And I could make that a constant flux instead of a constant value if I just do plus equals. Let's not do 75, 3. Okay, maybe not. Only integer or float. Maybe it doesn't support the plus equals operation. So maybe I'd have to do C equals, what is it gonna do if I don't give a single point? Yeah, well, I don't know, but it's possible somehow. So back to this, plenty of exercise. Now back to the tumor spheroid. So we kind of played about with the D and gamma. We saw that it actually changes the shape of the concentration, going from a linear line to a curved line, for instance. So if we set those properly and the uptake properly, we can have a proper profile in the tumor to have the several layers. we know that it is proliferating, quiescent, and necrotic. And we also know from biology how many cells thick each one of those are. So how many is that? I don't know, 4 cells thick for the proliferating. So if we set the uptake, diffusion, and decay properly so that the decay length inside the tumor is 4 tumor cells, we should have the structure, give or take. Where was I? Here. And we don't even need to care about the real values of the diffusion constant or decay constant, because we only care about the diffusion length. So we can set those so that we have the correct diffusion length, and we are golden. Say the real diffusion constant is 20, but I can very well make it 80 as long as I also up the decay by 4. So here was my slide on boundary conditions that we've talked about for a bit. That constant value, no matter what happens, it's going to be that. Constant flux, no matter what happens, it's going to change by that. Periodic goes around to the other side. And nothing changes is a special case of flux, where you have no flux. Well, nothing gets put in and nothing gets taken out. That's what I meant by not changing, because the environment might change the concentration there, but the border does nothing. So again, a conceptual table of what do we know about the model so far. Same objects, environment, and fields, but now the fields have more stuff, boundary conditions. We can also have the whole medium as a supplier instead of the borders. To do that, we use the secretion plugin that is pasted there with the with the diffusion. So here, secretion. I could add medium secretes X amount per time, or medium has X amount. If we have the medium as the source, the only source, and it is secreting a fixed amount each time step, if the tumor as the tumor grows, it's gonna destroy its supplier of oxygen and the supply of oxygen. So at some point, there's not gonna be enough oxygen coming in for it to stay alive. So it's gonna start to die from hypoxia. And you might even get a simulation that you get a oscillating tumor if you do it like that. We can calculate what the maximum size of the tumor would be. So if you have a medium of size L by L, each point in the medium upping the concentration by alpha, you're gonna change the concentration by alpha times the area of the medium. When you have the tumor there, the change in production, it's gonna be alpha times the difference in area of the medium and tumor. Since where the tumor is occupying, there's no production. So the steady maximum tumor size is gonna depend on the minimum consumption of the tumor, that I'm gonna assume that is proportional to its area as well. So another constant K times the area. And when what is consumed and what is produced are equal, you have the maximum tumor size with medium as producer. this, yeah, no, in this example, I'm talking about having the medium itself as the supplier of oxygen. For these calculations, it's supplying with constant flux. You can have the medium be the constant value supplier as well. The code example I have at the Google Drive, one of them is with medium as supplier, but constant value supplier. So these calculations are not valid for that because the CDT is 0 for protection. C is going to be, yeah, C itself is going to be that. Yeah, because that area is not medium any longer. So yeah, that's just a quick side note I had. But again, we can have the edges as the suppliers. Again, of constant flux or constant value. The advantages of edges is that they are going to be there no matter what happens. So you won't be able to destroy them. So it's safer. Yeah. Yeah, no, the edges are still going to be there because the edge is not even a pixel or voxel, it's the end. Yes, the side of the lattice. A thing I've noticed that with constant value, as the tumor reaches the edge, it might grow faster because its supply of oxygen is greater. If you imagine that you have a fixed value boundary and you have the tumor on it, it's going to have all the oxygen it could ever want because the concentration of oxygen is never going to change from whatever you set. And now we've added cells to the model element, to the model elements of different types. They're going to have a position in space, a volume, a color, some uptake, and that's all for the tumor. Oops, I went up instead of down. So yeah. What we mean by uptake is any use of the cells of the chemicals that are there, be it for energy, respiration, ligands, some chemoattracted that gets consumed, be it the cell eating, breaking it down, it just decaying because it's an organic molecule. Well, that's in the decay constant, but anyway. But you can't pack circles. We do have hexagonal lattice as well as square lattice. Oh, no, we don't have a circular boundary, but that's a good idea, maybe. Magic? Yeah, the problem would be with periodic boundary conditions, what happens then. But if we just don't allow periodic boundary conditions, then maybe we can have it. Yeah, yeah. Yeah, or you make the tumor way smaller than the, yeah. Yes. Yeah, using frozen cells, we can build walls, so you could build a circular wall and have that be the supplier as well with the secretion. Yeah, cells can secrete as well as uptake. Yeah.
But you can also, so you have a hexagonal, you said you have a hexagonal lattice.
Yes.
So could you also have a hexagonal box? You know what I mean? Because that would be periodic. That would be
Yeah.
compatible
Yeah.
hexagons.
Yeah, we don't have that, but yeah. Having a hexagonal domain. Yeah, that's also a good idea. Yeah. Okay. Oh, yeah. So for uptake, we could just naively assume that the cells consume X amount each time step. But what happens when the concentration is less than X is that concentration will go negative because we are on a computer and computers are dumb. And that would never happen in nature. So thankfully, CompuCell by default already, you have a fraction of concentration term for the uptake. So if it is less, it's going to multiply by that and everything is going to be fine. What we don't have in CompuCell is something like a saturated uptake, like Michael is mentioning here, with some kind of hill function that, okay, you have a uptake, but it reaches a maximum smoothly instead of just being a step as it is in CompuCell of having a straight line when it's less than the maximum you want and then the maximum you want. In a future version of CompuCell, we are going to have saturated uptake, but for now, we don't. Yeah, it could have a, no, you go through the lattice, then you have a flag that if you find anything below 0, you set that flag to true. Then you have a if statement that if that is true, end the simulation. Yes. What we can do in CompuCell for the saturated uptake is that you can set it by hand. So each time step, you could calculate what the saturation would be in a Michaelis Menten case and set that to be the value to be uptaken. Then you're good. But it's more work. Yeah. Yeah. And we also have uptake regions. It couldn't be that your whole cell is uptaking. It could be that it's uptaking on the border just outside itself, on the border just inside it, or on the center of mass. And since uptake is proportional to the area that you are uptaking from, the uptake values that you use should be rescaled if you want to change from one to the other. So here, I actually have another example. So that one is going to be in examples, uptake types, that one. There we go. So those cells are frozen. They're not going to change. And in this case, let me grab the project already. So in this case here, I'm setting up how much they're going to uptake. All of them are proliferating cells. I'm going to go into more detail on this when we actually go to the tumor, because this simulation I did after the other one. So here are all the options for uptake. You have the cell that is uptaking. So right now I'm going through all of the proliferating cells. So I have the cell that is uptaking, how much it uptakes, and how much it uptakes if the concentration is less than what it wants. And it's uptaking inside the whole cell. Here's the option for inside the cell at boundary and outside the cell at boundary and at center of mass. Oh, so say you're trying to uptake 10 every time step. One time step you have 15, you're good. So you take 10 out. The next time step you have only 5. So that's not enough. So the relative uptake comes in and it multiplies the concentration you're at by that. So let's say your relative uptake is 0.2 and you have 5, then you're going to consume 1. Yeah, it changes the uptake rate. But then you need to take care of those cases by hand. Yeah, yeah. Yeah, but yeah, you can use the secretion plugin. Just secrete a negative amount, yes. So here is what happens with the concentration profile. If the cells are uptaking over the whole thing and the supply is coming from the edges, well, it goes down to a bell curve pretty neatly, and the concentration profile goes further away than the end of the cells. I'm gonna add another plot here just with the cells. So we can see that there's a change in concentration outside the region the cells are in. And that's because the supply is coming from the edges. If the medium were supplier, that wouldn't be the case because the concentration would stay constant until you got to the cells that are consuming everything, and then it would go into the valley. But, oops. No, this was an example just to exemplify this. So this is going to stabilize probably. Yeah, it's going to be 2 lines going to 0 at the border in this case. And it reached 0 pretty fast. But there are the other options here. If I just comment that secretor and uncomment this one, now they're gonna consume just inside themselves at the border. So let me just do one step. Because, there we go. So we can already see that they consume just inside the border from the color scheme. If I zoom in, you can see the border of the cells here and the blue area inside those borders.